Hello, my name is Daniel and I will present some quantic explication. I make this video in 2004 when I was studying at Polytechnic Bucharest. I had this video on my computer and in order to not delete it, I decided to share it on YouTube. Here we can see some structure molecular. Here we have a list with some constant and Mendeleev table. This is the polonium structure as cubic simple. List with materials that have a network cubic volume concentrated where it has node and the space between atoms name interstice. Network constant name it with A and the reticular plane we can see there. List with materials that have CFC. This is the elementary cells for crystalline network. List with materials that have compact hexagon. We can see some examples with impurities added between interstices. If a molecule is taken out, then we can see Schottky defect formula. Here is the Frankel defect free node and occupy interstice. Atom mass is measured in kilomole. Inside in atom we can imagine particular named Ion. Ion is a popular name in Romania. Trăiască nea Ion. Let's go back. Okay, electrons quasi-free interact with other ions and free electrons move from interspace. Bounded electrons by Coulombian force orbiting on the principal layer of core from K to Q. Why they chosen this enumeration? Okay. Spin motion of electron will result a magnetic torque, Pauli principle. In the middle we can see the core. Also inside the core we can see the protons and neutrons that are orbiting in the center of the atomic core on the layers enumerated from A to G. Discussing the microplane, we can make an analogy with our solar system. We can see some formula with the length between two collision of the electron and drift speed. First wave, second wave, third wave, and so on. Broglie say that the amplitude of the wave associated with the electrons is the wave or the depth of the radiation penetration. The collision of the electrons with ions will generate an energy. Above is a static Fermi-Dirac with half integer and anti-symmetric spinings, and below is the static Bose-Einstein with integer and symmetric spins. When an electric force is applied, it pushes electrons, directing their spin towards its direction, showing like a tail comment. Particle cannot orbiting in the image. The heater London function tell when bounded electron with their associating wave after the collision system will result. As a result of interaction, some potential energy result. Simple. Upon interaction, the energy increases towards the higher levels, but the energy bands remain unchanged. We can say that the bonds increase and the space between them decrease. In the Schrödinger equation, the approximation of free electrons does not interact with ions. The abscissa is a 0x axis along the length of the crystal, and the ordinate is the function associated with the electrons. The cyclicity condition of Born, attention, not Bohr, was Max Born. We can see the wave with each amplitude. Quasi-free electrons interact with ions, and with each collision, also called Bragg reflection, they decrease their energy. Harmonic energy in order n and concentration of quasi-free electrons. A Bragg reflection details. About the insulators, the electron on the last layer give us the valence number, and their energy is in last allowed band or valence, and cannot pass into the first allowed band or conduction. Energy is far from the Fermi band gap prohibited. The electron's energy decreases with increasing temperature. Electrons do not pass from the valence band to the conduction band, but their energy due to thermal agitation leaving a particle called a hole or empty in the valence band. Electrons and holes give each other an electrical current having identical charge. In the image, we see a semiconductor. An extrinsic donor semiconductor gives the impurity, thus it means electrons goes up a valence that become quasi-free. Its energy easily passed into conduction band. Here we have an acceptor semiconductor with lower valence impurity that accept the valence electrons, thus keep its energy in the valence band. Monovalent metals. That's it. Most conductors have the conduction band totally above the valence band. If we increase the temperature, then the energy increase towards the upper layers. Those become some superconductors. 1s2 is the higher layer. Electron spinning. Bivalent metals have conduction band partially over valence band. The energy of the electron easily passes into conduction band. We can see when the temperature decrease, the energy will increase. Let's see what happens when we turn on a consumer, like bulb, for example. Electrons flow, but attention, from minus to plus because their charge is negative. Electrical conductivity of metals is the inverse of electrical resistivity. Electrical conductivity decreases when the temperature increases. Electrons lose their energy and speed. Ions oscillated in 3 dimensions. What we call the corona effect are thermal and acoustic waves that appear at high voltage. When the temperature increases, the energy of the ions will increase, and if apply an intensity of electric field, the electrons will suffer collision, thus the conductivity will decrease. In the center we can see a shock wave. The longitudinal thermal wave has elongation Y. K is Boltzmann constant there. The electron approaches, it looks like a spermatozoon or like a comet. Increase the energy of the electron near the ion collision. In a collision, the wave of electron will have one reflected and one refracted. The mean free path and the relaxation time decrease. It results that the conductivity will decrease. Heisenberg principle. Electron lose energy in the first collision, but gain another energy in the second collision. If an electric force is applied, the electrons will perform mechanical work. The conductivity decrease hyperbolical up to Debye temperature. The conductivity decrease in relation to the increase in the number of impurities. Determine electron breaking. Conductivity decrease when the state of aggregation change from solid to liquid. We can see a melt cable. If the temperature increase, the lattice constant increase, ions oscillated increase, the middle part between two collision decrease. Respectively, the relaxation time and conductivity decrease. If a mechanical treatments are applied, then defects appear in the network with extra collision and the conductivity decrease. In the area where the ions comes closer to increase the allowed bonds, more collision and the conductivity decrease. With a micrometer we can generate 100 amperes through the metal plate, measuring its voltage and resistance, and then according to classic formula we find the resistivity. Metal plate is in helium enclosure. Meissner effect say if between two magnets or electromagnets we have a magnetic field, if the temperature drops to absolute zero, the magnetic waves bypass the metal and the metal from field. The effect of frequencies. The field lines are explained when it becomes superconducting and return the frequency is higher than 10 megahertz. The isotopic mass increase and the temperature decrease. In the situation when the intensity of electric field is higher than the critical one, then the conductivity is cancelled. In the graph we see how the amplitude of the signal increase. In the helium enclosure we have the Johnson junction. Contain layers. First is tin or lead. Second is tin oxide and lead oxide. Third is glass junction. And 4 and 5 like the first and second. When the temperature is lower than the critical one, electrons get generated on the outside glass of junction. When the current is bigger than the critical one and this voltage is higher than the critical one, the junction loses its superconductivity. Capturing the magnetic flux outside the ring will generate a flux inside. Below we can see the London equation. In the ring section, the field will generate focal current. The BCS theory, Barden, Cooper and Schrieffer say that pair of two electrons with lower energy than the normal one is called copperon. After the collision, the first electrons leaves a potential hole, the second fall into it and forming an attractive force between them. Interesting. The distance between is called coherence length. The pair has the entire spin, so it will respect Bose-Einstein theory. The copper no longer collides with the lattice. It has double mass and opposite spins. A list of superconducting materials, unfortunately, are in the form of powders. I switch it to semiconductors. Network of silicon atoms, silicon and germanium are the most used semiconductors. Silicons have 4 valence electrons forming valence electron with its neighbors. The thermal wave breaks a bound resulting to quasi-free electrons. The energy passes from the valence band to conduction. 2 gaps remain in the valence band, the red spheres. Not the electrons, but their energy passes into the valence band into conduction. Energy due to thermal agitation leaves a particle called holes and the valence on the valence band. The charge carriers give each other electric current. Conduction band of the intrinsic of impurity-free semiconductors. In the case of intrinsic n-type semiconductor electron donor, we can add phosphorus. It has a plus electron. Phosphorus give up higher valence electrons that become quasi-free with the energy passing easily into the conduction band. With the yellow we see the donor level. In the case of extrinsic p-type semiconductor electron acceptor, we can add boron. It has a minus electron. Boron has lower valence and the impurity accepts of valence electrons from the semiconductor, keeping the energy in the valence band of the hole. With green we see the acceptor level. The PN junction of the unpowered diode has a zero thickness, L. If we feed with direct polarization, we will have conduction. If we feed with reverse polarization, we will not have conduction. N side emit only electrons and P side only holes. What ugly image. To measure an electromagnetic fields, we need a Tesla meter with a Hall probe put in a magnetized device. Feel a line of the residual induction from north to south. The Hall probe is a direct powered semiconductor. Intensity E and current E have the same vector directing, and the electrical force is in reverse. If we approach with a magnet field that has a magnetic induction vector upwards with the corkscrew rules, we rotate A over B, we'll see the direction of the Lorentz force vector. Hall force and intensity appear, resulting in the Hall voltage, which we can measure and which is proportional to the magnetic induction. At equilibrium, when the forces are equal, we will have equal potential. When the magnetic induction increases, the Hall voltage will also increase. Anyway, if you want to see more presentation like this, read me in the comments and see you next time. Bye.